take those minutes to just quickly introduce the first topic that we'll really delve into in the next lecture. So we're going to talk about incidence of taxes. Let me give you an outline of what this set of lectures will look like to start, and then just introduce the topics a little bit. So we're going to start with a definition of incidence and an introduction to the topic. We will then talk about incidence in a series of steps. The simplest way to think about incidence is partial equilibrium, so that's one market at a time, rather than thinking about all the feedback effects that might occur in general equilibrium. Then we'll bring in right away the behavioral elements that seem to matter. So there's growing evidence that people don't really seem to pay attention to taxes. And so we'll talk about how incidence works when only some agents are paying attention to taxes and how that affects incidence in practice. We'll then talk about a bunch of empirical applications of the partial equilibrium incidence methodology. There's a ton of empirical work on this sort of thing. And in that context, you'll start to see some of these empirical methods that I was describing earlier. We'll then talk about incidence in general equilibrium, which is a much more theoretical or simulation-based literature, because one of the fundamental challenges in empirical work is that we know how to do partial equilibrium type of stuff well, but we don't really know how to do general equilibrium empirical work well. And why is that? Because the basic paradigm that we use for empirical work now is a treatment-control comparison. So one group, let's say one state gets a tax change, or higher income people get a tax change and lower income people don't. We compare the behavior of the two. That doesn't work in general equilibrium because the whole point of general equilibrium is that the control group is also affected. So you immediately have contamination. And so one of the, I think, grand challenges in applied microeconomics is figuring out how to do empirical work that gets at general equilibrium effects. We'll then talk about two techniques to solve, a technique that solves that problem, which is capitalization. And then we'll talk about another set of issues related to mandated benefits. So for this set of topics, for the classic theory, you can look at the Kodlikoff and Summers handbook chapter. You can look at the old Atkinson and Stiglitz text. And then you can look at this recent paper with Looney and Croft that deals with these behavioral issues, but also provides a very simple introduction to basic issues in tax incidence as well. So that could also be a good place to start. So ideally, you would have looked through some of this stuff before the next lecture so that you get the most out of it. Let me just give you a definition here and then organize what we'll talk about. So tax incidence is the study of the effects of tax policies on prices and the distribution of utilities. Okay, so incidence is about how the pie gets split across people in the economy. Efficiency is about the size of the pie. Okay, so we draw that sharp distinction between the impacts of any policy, incidence and efficiency. So what happens, the way it's typically analyzed is what happens to market prices when a tax is introduced or changed. So for instance, one of the empirical examples we'll talk about is increasing the tax on cigarettes. Who ends up bearing the incidence of that increase? Now, at some level, the answer is very simple. Like if I charge consumers a $1 tax to buy a pack of cigarettes, they have to pay $1 more. But that's clearly not the ultimate answer because prices could end up changing in equilibrium where manufacturers lower prices so that they can sell more cigarettes, right, even after the tax has been implemented. So the tax could end up being borne by the producers or it could end up being borne by the consumers. And you can see why it's quite important to figure out who's actually paying for this tax. Similarly, the introduction of the Earned Income Tax Credit. Well, Earned Income Tax Credit is billed as this great program that's giving money to low-income individuals. But we're going to talk about a paper which shows that one of the impacts of the Earned Income Tax Credit is that companies like Walmart now pay people lower wages because they know that they're getting the EITC. So what's the logic? You come to work at a Walmart job. Now, let's say I was getting paid $10 an hour. Now with the EITC, I'm getting paid $14 an hour. So a lot more people want to work. Walmart says, well, lots of people are willing to work now even at a lower wage rate of $8 per hour. I can cut the wage rate to $8 per hour and still get the same number of workers because all these people are happy to work. And so what ends up happening is that a good chunk of that $50 billion ends up going to Walmart or companies like Walmart rather than the workers whom you're presumably targeting. And you can see why that's very important for figuring out whether you want to have this policy. Similar issues with the food stamps program, right? Who's bearing the incidence of food stamps? And so what we'll talk about is the distributional effects of these types of price changes on all of these various agents in the economy, both theoretically and through a series of empirical examples. So I'll stop there for today. Right, so today we are going to talk about tax incidence. Let me just start by refreshing your memory where we left off in the last lecture. We were talking about economic versus statutory incidence. So what we mean by statutory incidence is where the tax actually falls. So if I tax a consumer and the consumer actually has to pay the money to the IRS, we'd say the statutory incidence of that tax is on the consumer. But the key point and the whole idea of this section of the class is that economic incidence need not be the same thing as statutory incidence, and in general won't be. So consider, for example, to see why this is important, the following argument. So many people think that the government should tax capital income more, like capital gains, dividends, interest income, because it's concentrated at the very high end of the income distribution, right? So you hear, for instance, that Mitt Romney paid an average tax rate of 13% on his income, and many people think maybe we should have higher tax rates on people like him who are earning a lot of capital income. But that argument is basically one that's based on statutory incidence and does not think about economic incidence, in particular neglects general equilibrium price effects. So it's quite possible that in equilibrium, what firms do when they're taxed more heavily on capital is lower workers' wages. So we'll see how this can work out in a market clearing equilibrium. And so, for instance, if higher capital taxes lead to less savings and capital flight, so that means like companies, instead of investing in the US, invest in other countries with lower corporate tax rates or capital tax rates, then the capital stock might decline. That drives the return to capital up and may drive wages down in equilibrium, all right? And so some people actually argue that capital taxes on net end up being paid by workers rather than capital owners, and thus might end up increasing income inequality rather than reducing it. So you can see how figuring this out is very important because before you can make distributional statements about the distributional impacts of policies. So tax incidence is an example of what we call positive analysis, which we mentioned in the last lecture. It's typically the first step in policy evaluation as an input into thinking about which policies maximize social welfare. So this entire next couple of lectures is going to be totally positive, totally descriptive of what taxes actually do to prices in equilibrium. Now you'll see that the theory is informative about signs and comparative statics, that is in what environments we should expect more of the incidence to fall on consumers versus producers, for example, but it's completely inconclusive about magnitudes. So is 100% of the incidence of a capital tax going to fall on workers or 0% going to fall on workers? We basically are not going to be able to tell from theory. And so what ends up being important are some parameters which are generally related to elasticities of supply and demand. So one of the examples we'll talk about today is the incidence of a cigarette tax. And there, the elasticity of demand with respect to the price of cigarettes is going to be crucial for determining the incidence of that tax. Another example that we've just been mentioning is labor versus capital taxation. Here, the mobility of labor and the mobility of capital are going to be critical. How easily can companies shift operations to other lower tax places and so forth? Okay, so ideally, we would characterize the effect of a tax change on utility levels of all agents in an economy, right? We'd go agent by agent, and we'd say, how does this tax change affect each person's welfare? That's sort of the ultimate objective of incidence analysis. Now, in practice, that's very difficult to do, and so a useful simplification, which people always make in this literature, is to aggregate economic agents into a few major groups. So, for instance, you might analyze incidence at the level of producer versus consumer, as in this tax on cigarettes that we're going to talk about. You might analyze it at the level of the source of income. Are you a worker or are you a capital owner? You might do a distributional incidence by level of income, so higher income versus lower income people. You might do it at a spatial level, so how do local property taxes affect different regions in the country? Or you might, for instance, do it across generations. So in the Social Security literature, This is very important because as you think about Social Security reforms, you end up transferring money from one generation to another generation. So we'll see a few examples of each of these different types of incidence analysis. So let's start with the most basic framework, which is a partial equilibrium model of incidence. And let me be precise about what the key assumptions are in this model, in using a partial equilibrium approach. So the first and most important assumption is that we're going to assume that there are only two goods in the economy. So what that means is that there's only one relative price. So let's say we have apples and oranges. There's only going to be one relative price between those two. And so you can see immediately that that's going to eliminate all general equilibrium concerns. Or to put it differently, partial and general equilibrium are the same thing when there's only one price that's moving around. So what we're abstracting from in this initial partial equilibrium analysis is the problem that when I change prices on one good, when I change taxes on one good, prices of all the goods in the economy in principle might change, right? So if I put a tax on apples, not only is the price of apples going to change, but the price of various other fruits might change, and the price of the wage rates that people who pick apples are going to change, et cetera, right? So there are many prices to keep track of. Here we're basically eliminating that problem by assumption. Now, of course, in practice, we're never in a case where there are only two goods. So while this is technically the right way to state what we're doing, it's useful to think about the partial equilibrium approach as an approximation of incidence in a general multi-good model under two conditions. The first is that the market being taxed has to be very small. So if we think about a tax on labor income, that's not a very good assumption because we think that taxes on labor income are so large that they're going to have income effects that demand ends up being shifted for all the products in the economy and all prices might change. If in contrast you're thinking about a tax like on chewing gum or something, it's unlikely that a tax on chewing gum is going to affect equilibrium wage rates because income effects are so small from that market is so small, and so it's more plausible to use a partial equilibrium approach. The second assumption that you need is that you might have strong spillover effects to other markets if there are complementarities in the utility function, right? So if the number of cars I buy is closely related to the amount of gasoline that I consume, then of course a tax on gas is going to affect car demand, even if the gas is not a big share of the budget. So in general, the idea here is that taxes can have spillover effects on other markets through income effects or through direct complementarities in the utility function, and we want to eliminate both of these in this initial analysis. And so this first assumption gets rid of the income effects. The second assumption gets rid of the direct substitution. Okay. The second assumption that we make is that the tax revenue that the government collects is not spent on the taxed good itself. So if we're thinking about this tax on cigarettes, we can't have the government then taking the money that it collects and buying cigarettes itself, because that's going to end up affecting the equilibrium price. So typically what we assume is that the tax revenue is used to buy the untaxed good, or a common assumption is that it's thrown in the ocean, right, and has no impact on the economy, which obviously is a simplification. And then the third assumption, which is actually not critical for the partial equilibrium approach, but is going to affect the formulas that we derive, is that we assume that there's perfect competition among producers. So you can relax this by allowing for monopolistic competition or oligopolistic competition, but we're not going to do that in this lecture here. So it's really the first assumption that's conceptually important. Okay, so with that set up, any questions about the basic assumptions? Okay. With that set up, let's now take this case where we have two goods, which we're going to call X and Y. Let's assume that the government levies an excise tax on good X. So in the literature, people distinguish between two types of taxes. What's called an excise or specific tax is a tax that's levied on a quantity. So if it's like $1 per pack of cigarettes, I'd call that an excise tax. But if it's a percentage tax, a percentage of the price of the good, we call that an ad valorem tax, and the most familiar one is the sales tax, like 5% of the price you pay, right? So the excise tax, we're going to focus on the excise tax because the math is slightly simpler because you're adding something instead of having a product, but it's basically the same logic. So let's let P denote the pre-tax price of X, and Q equals P plus T, T is this excise tax, denote the tax inclusive price of the good. And good Y, the numeraire, is going to be untaxed. So what do I mean by the numeraire? We're normalizing the price of good Y to be 1, right? And we're holding that fixed. So the only relative price in this economy is Q. So the consumer has wealth Z, which we're going to take as fixed, and a utility function U of XY. And let's let epsilon sub D denote the elasticity of demand with respect to the price. So this can be written in a couple of ways. Hopefully this is familiar to most of you. It's just the slope of the demand curve times the price divided by the level of demand, the quantity. Or another way to think about this is that it's d log d, d log q. So let me just mention here that this is a useful, sorry, this is not great. But can you see this? Not really? Let's see how this works. I think it's the first time this board has ever been used. Okay, that's better. So actually, let's make that a minus. Okay, so it's the same thing as. Okay, so a very standard assumption in empirical studies is that the demand curve is log linear. So that is, it's linear in logs of quantity and price. And so then that coefficient on log Q is going to be the price elasticity of demand, right? And so what are we basically assuming there? We're assuming that the demand curve looks isoelastic, right? So if we have price and quantity, rather than assuming that the demand curve is linear like this, if it's linear in price quantity space, the elasticity is going to be changing as you go down that demand curve, right? So instead, we assume that it has an isoelastic form, so that in log space, if I plot log, and sorry, the notation is not great here. So this is D, okay? So prices are on the y-axis. The tax inclusive price is what I was calling Q. Okay, so call that Q equals P plus T. And so then let's plot log Q versus log D. We usually assume that the demand curve is linear in log-log space, okay? And that's convenient because usually we tend to think that price elasticities are roughly constant, and we'll see various examples of this. There's no mathematical reason that that has to be true. But assuming a constant price elasticity is often analytically convenient and appears to be a good empirical approximation. And this specification is going to generate that constant elasticity. Now, one thing you should note, which is useful to keep in mind as you work on these applied models, is what types of utility functions generate the demand function that we're going to be working with. So usually we start in public finance, often in empirical studies, by just positing what the demand function is. But you know from basic microtheory that any demand function that satisfies certain regularity conditions can be generated from some utility function. So that's the recoverability. And so in this case, the utility function, you can work this out at home, is going to look something like this. Okay, so this type of form where we have this concave utility function that looks like that is going to generate an isoelastic demand curve. And you'll see that pop up very often in this class and in many applications. So that's what's in the background here when we write down this demand curve. But what I'm going to show you here is not going to actually depend upon what that utility function looks like. But it's useful to be familiar with this basic structure because of how often it's used. Any questions on that? Okay, so what's the interpretation of the elasticity? It's the percentage change in quantity when the price changes by 1%. And that's a widely used concept because elasticities are unit free, right? If I just tell you the slope, then I need to know the units in which you're measuring the number of cigarettes or whatever. Okay, so now let's think about the supply side. We're going to assume that firms are price takers. This is the perfect competition assumption. And to be precise, we're going to say that firms convert the numeraire good Y into units of X. Okay, so they're basically converting one good into the other, And in particular, they use C of S units of the numeraire to produce S units of good X. And we're going to make the standard assumption that the cost of production is increasing and convex so that you get to an interior optimum. So C prime of S greater than 0, that's just, it costs more to produce more, and then the marginal cost of production is increasing. The profit that a firm earns given a pre-tax price of P and a level of supply S is just then P times S, the amount of revenue it generates minus the cost of that level of production. With perfect optimization and perfect competition, the supply function for good X is implicitly defined then by this marginal condition. So the firm is maximizing profits. It's going to supply up to the point where the marginal cost of production equals the price. And we know that that's going to define an upward sloping supply curve, right? Given the assumption that marginal costs are increasing. And let's analogously let epsilon S denote the price elasticity of supply. Okay? So that's the very simple setup. Now we have an equilibrium condition, which is market clearing. So the quantity, the equilibrium quantity, has to equal the amount that's supplied at the pre-tax price, which has to equal the amount that is demanded at the tax-inclusive price. Remember that we're assuming that the statutory incidence of the tax falls on the consumer. And that is going to implicitly define an equation, P of T. So if I give you a T, I'm going to be able to solve this model to figure out what the equilibrium price is, right? Because I know what the supply curve is, I know what the demand curve is, and I can solve for the equilibrium price. So there's going to be some function P of T, and the goal of incidence analysis is to characterize dP dt mathematically. Okay? That's the effect of a tax increase on price. So first, we're going to go through some graphical examples, which hopefully will be familiar from an undergraduate economics class, and then we'll analytically derive some formulas and talk about their properties. Okay, so here's the simplest graph. First, take a market where the initial equilibrium is at A, where supply equals demand here, at a quantity of 1,500, say, and a price of $22.50. Now, suppose we levy a tax of $7.50. What happens? The demand curve shifts inward by $7.50. What's the logic? My willingness to pay for this 1,500th unit of the good now falls to $15 instead of $22.50 because I've got to pay $7.50 to the government, right? So my first order condition for utility maximizing consumer is going to imply that I want to buy only 1,500 units of the good at a price of $15. All right, so then now what is the new equilibrium? It's the intersection of supply and demand with the red curve and the supply curve, which hasn't changed. And so that's going to bring us to point D. What do we see here? We see that the incidence of the tax is shared between the consumer and the producer, right? So the supplier previously was selling the product at $22.50, but now is selling it only at $19.50, so he's taken a hit of $3. And the consumer is now paying $27 for the good instead of $22.50. So you can see right away that the statutory incidence is not the same as the economic incidence. What's the logic for why the price changes? Well, the supplier realizes that he's not going to be able to sell a profit maximizing level of output unless he cuts the price given the inward shift in demand. And so it ends up being that, in this particular numerical example, he wants to cut the price by $3 in order to meet the market clearing condition. Okay? So now you can see that it works the same way if we have the tax levied on the supplier instead of the consumer, where we have the supply curve shifting inward in this case. And the key thing that you can see from this graph is that in the standard neoclassical model, the incidence of the tax, the economic incidence, does not depend upon whether the tax is levied on the consumer or the producer. So notice that the numbers here are exactly the same. The supplier burden ends up being $3, the consumer burden ends up being $4.50. The idea is that if prices are free to shift in equilibrium, it makes no difference who actually has to pay the tax authority at the end of the day. Okay? And you can verify that algebraically very easily. Now, what are the comparative statics of incidence? So what are the situations where a consumer pays more and a producer pays more? it all depends on the relative elasticities. So we can see that by looking at some extreme examples. So take the case of perfectly inelastic demand, where the consumer wants to buy 1,500 units of the good no matter what the price is. So then what's the burden of the tax going to be? The incidence of the tax falls entirely on the consumer in this case, right? Because the consumer is totally inelastic. So what's the intuition for that? The way to think about the logic of incidence is that the supplier needs to change prices in order to clear the market. Now, if the consumer is going to demand the same number of units of the good no matter what the price is, the supplier doesn't need to change his pre-tax price at all in order to continue to clear the market, right? So think about like the case of a prescription drug, which I want to buy no matter what the price is. If the government levies a $10 tax, the market is still going to clear if total prices rise by $10. There's no reason for suppliers to cut price. So in the case of perfectly inelastic demand, the consumers are going to bear the tax entirely. Conversely, if demand is perfectly elastic, so take, for instance, the case of two virtually identical products. And so I don't really care if I'm buying product A or product B, and we levy a tax on product A. Then everybody just shifts to product B. And so in order to make the market clear, the supplier really cannot increase the price of product A at all when it's taxed. Otherwise, he's going to lose the entire market. And so as a result, when demand is perfectly elastic, the incidence of the tax falls entirely on the supplier. That is, the supplier has to cut the price by an amount equivalent to the tax. Okay, and then you can think about the intermediate cases. What does this illustrate? The more elastic factor is going to end up bearing less of the incidence of a tax. And that's a general principle that we will see in many applications. Okay, so let's now talk about how we compute numerically what the incidence of a tax is by deriving a simple formula. So the equilibrium condition in this market is that demand at the tax-inclusive price has to equal supply at the pre-tax price. And that, as we said, implicitly defines an equation for P as a function of T. So let's implicitly differentiate that equilibrium condition to obtain this expression. And I'll let you work through the algebra at home, which is straightforward. So dP dt is going to be given by the slope of the demand curve, dd dp, times 1 over the sum of the slopes of the supply and demand curve. Okay, so why do I say sum of the slopes even though there's a minus sign here? Because the demand curve is downward sloping, right? So it's a negative number. All right, so we'll talk about the intuition for why you get that particular expression in a second, but notice that you can rewrite this expression here in terms of elasticities, just by multiplying through by the ratio of price to quantity. And so you get this simple expression for the incidence of a tax on the supplier, which is the ratio of the demand elasticity to the sum of the supply and demand elasticities. And then conversely, what's the incidence of the tax on the consumer? Well, that's just 1 plus the incidence of the tax on the producer, because remember, the consumer price is just P plus T, right? So dP plus T dt is just 1 plus dP dt. And that's going to end up being the elasticity of supply divided by the sum of the elasticities. So right away, you can see from these formulas that the more elastic factor bears less of the incidence of the tax. So for example, if the demand elasticity is 0, so demand is completely inelastic, suppliers end up bearing none of the incidence of the tax, exactly as we saw in the previous example. Right, let's look graphically at why we get this particular formula, which is going to be useful for the next thing that we talk about. So here's the way I like to think about incidence. There are basically 2 steps in determining equilibrium price incidence. So the first thing to note is that when we levy the tax, the demand curve shifts inward, and suppose for a moment that suppliers decide not to change prices at all. They just ignore the fact that this tax was levied. So what they're going to find is that they have an excess supply or an excess inventory of goods, right? Because they're going to be supplying this much, but people are only buying that much. And so what's the size of this gap, or what's the size of the excess supply? Well, it's just given by the size of the tax change, which we're going to call dt, the size of the tax we introduced, right? times the slope of the demand curve, because that's going to determine how much less consumers want to buy. So if I levy a 10-cent tax and DP is given by some amount, I multiply the 10 cents by that amount to figure out how much demand has fallen. Okay, so that brings me to this point. Now what I need to figure out as the supplier is how much do I need to cut price in order to re-equilibrate the market, right? In order to clear all my inventory. And so that, if you just look at this graph, is going to be given by, I take the size of the excess supply and divide it by the sum of the slopes of the red and blue curves. And that's going to determine how much I need to cut the price before I get back to the point where the two intersect. And so that's why you end up getting this expression here, where the incidence of the tax is given by the slope of the demand curve, given by the sum of the slopes of the supply and demand curve. Okay, so it's quite intuitive that that's what that expression looks like. Questions? Okay, so let's now talk about a variant of this very simple theory that goes back a long time. So what's a critical assumption of the neoclassical model that we started out with? It's that taxes are equivalent to prices, right? When I raise the tax on a good by $1, it has exactly the same effect as increasing the price of a good by $1, which when you're thinking about optimizing makes perfect sense. Why would you care if you have to pay $10 for a good as an optimizing consumer, why would you care if the extra dollar is going to the government or to the producer, right? You should only care about the gross tax inclusive price. Now, there's a recent literature which asks and really questions this assumption by presenting quite a bit of evidence that people do not really seem to be fully aware of tax rates. So if you think, for example, of doing a simple survey of asking people, are you aware, what is your marginal income tax rate? If you earn an extra dollar, how much are you going to have to pay to the government? Many people really have no idea. You ask people about what taxes look like on particular commodities, or maybe even more importantly, when you're buying something, do you really pay attention to what the tax on that good is? And often you find that people don't seem to really be fully aware of what these taxes look like. And so I'll present some empirical evidence on this in a minute, but let's run with that for a second. And so what we do in this paper I'm going to talk about now, which you can kind of see that there's an empirical part and a theoretical part. The theoretical part, tying back to what we were just discussing, is updating the traditional theory of incidence to account for this salience effect, okay? So what we're going to do in this paper is test this assumption. I'll present some evidence that people are not fully aware of marginal tax rates, and then generalize the theory that we've been talking about to allow for salience effects, okay? So 2 parts. The first part is testing whether this, what I'm going to call the salience of a tax, think of that as the visibility of the tax inclusive price of a good, affects behavioral responses to commodity taxation. And so the way we're going to formalize that is very simple. Does the effect of a tax on demand depend upon whether it's included in the posted price that you see on the shelf of a grocery store or on a restaurant menu, for example? And then in the second part, we're going to develop formulas for incidence and efficiency costs of taxation that permit these salience effects as well as other optimization errors. So let's start with the empirical work. We're going to structure the empirical work using a model that's a slight variant of what we've just been discussing. So again, we take the case with the two-good economy. It's a partial equilibrium analysis. We're going to let y be the numeraire and let p denote the fixed pre-tax price of x. Okay, so just to keep things simple here, in the empirical analysis, we're going to look at quantities. And just to simplify, we're going to assume that the supply curve is flat, that the marginal cost of production is constant, so that the incidence of the tax is going to fall entirely on the consumer. And then we will, obviously, when we talk about the theory of incidence, we're going to relax that assumption and talk about how the incidence of the tax depends upon the relative elasticities again. Okay, so, but just to motivate this empirical framework, just assume that P is fixed. So we're going to allow for a tax on good X, which is an ad valorem sales tax. And then we're going to assume that the numeraire good Y is untaxed. And the key thing that we're going to assume is that this tax on good X is not included in the posted price, right? And you'll see why that matters. So the tax inclusive price of good X, Q, is given by 1 plus tau times P. So this is an ad valorem tax, right? Like if the sales tax rate is 5%, it's going to be 1.05 times the price. And we're going to let the demand for good X be denoted by X of P comma tau, right? So that's a simple notational thing, but notice how it's different from the standard model where we usually write X of P plus tau. We're automatically assuming that dx dp equals dx d tau, right? The tax and the price have the same effect if this is a specific tax. But here the point is we're going to write it like this so that we allow dx dp not equal to dx d tau, and that's precisely what we're interested in testing. Okay. So if agents optimize perfectly, then demand should depend only on the total tax-inclusive price of a good. So what we should see in an optimizing model is X of P comma tau equals X of 1 plus tau P comma 0, right, with this notation. And a consequence of that is that full optimization implies that the price elasticity equals the gross of tax elasticity. So just think about differentiating these two expressions. If I define the price elasticity as d log x d log p as before, and I define what I call the gross of tax elasticity with this ad valorem tax as d log x d log 1 plus tau, if you look at this equation here, because they enter as a product, both of those elasticities should be the same, right? So if I increase the price by 10% or I increase 1 plus tau by 10%, it has the same net effect on P times 1 plus tau, so I should see exactly the same impact on demand. So the way we're going to test this hypothesis is to log linearize the demand function. So all that means is, one way to think about it is we just assume that the demand function has this log linear form, or another way to think about it is start from whatever demand function you want and take a log Taylor approximation in logs. Okay, it's basically the same thing. And you obtain, you're going to obtain this estimating equation. Okay, so remember we're allowing for different effects of taxes and prices. So this first part here, beta log p, is exactly like the log linear demand equation that I wrote up here, the traditional one. But then we have this additional term, theta beta log 1 plus tau, where in the standard model you would not have that theta term. You'd have the same coefficient on the two. But now we're allowing for this term theta, which is a different effect of the tax relative to the price. And theta can be interpreted as the degree to which agents underreact to a tax relative to a price. So if I can define theta as the ratio of the gross of tax elasticity to the price elasticity, right? If you just look at this equation, right? It's the theta is the ratio of the regression coefficient on log 1 plus tau to the regression coefficient on the price. And so one way to think about it is how much do people underreact to a tax change relative to a price change. Okay, so our goal is to estimate that theta parameter, and in particular test if it's equal to 1 or not, right? The neoclassical model would predict theta equals 1. So we have two strategies to estimate theta. The first is what we call manipulating tax salience. So that is to make the sales tax as visible as the pre-tax price. So to see how this works, let's call V the effect of this intervention that I'm going to show you, where we directly change the way in which prices are displayed. Let's call V the effect of that intervention on demand. So what's the effect in the notation of this simple model? The effect of that intervention, what is it in terms, in log terms? So this is the level of demand that we're seeing for the good given the tax as it's currently posted, which is, think of a sales tax in the US. When you buy something at the grocery store, the price that you see does not include the sales tax that you pay at the register, right? So this tax is being levied, but it's not salient to you in that sense. Okay, so that's the current level of demand, but I'm going to conduct an intervention where I show you the tax inclusive price, and so your demand is going to change in the notation of the model to this, and the effect of the intervention, the direct treatment effect, is going to be given by the difference between those two terms. So how do we map the impact of that intervention to the parameter that we're interested in estimating? So this is, I think, like the first example you see in this course of trying to go from the types of treatment effects that we commonly estimate in labor economics or applied econometrics to a parameter that is actually relevant in the context of a theoretical model for thinking about incidence and efficiency costs. What I'm going to show you is that this theta parameter is actually the critical thing that you want to know to understand incidence and efficiency costs. So it's useful to know how to estimate, to map this thing to that parameter. Okay, so conceptually what you want to do, and you can work out the algebra later, is compare the effect of this intervention to an equivalent price increase in order to estimate theta. So let me give you an example. Suppose the sales tax rate is 8%, okay? And I make the sales tax visible, and I see that demand fell by, let's say, 4% for the product when I made the sales tax visible. Now, another intervention that I can think about is what would happen if I raised prices by 8%. That is the amount of the sales tax. If I found that demand would have fallen by, say, 4% as a result of that price increase, I can conclude that everybody wasn't paying attention to the tax, right? Because the impact of the intervention of making the tax fully visible was equivalent to increasing the price by the amount of the sales tax. More generally, if I find that the impact of the intervention is half as large as a price increase of the size of the sales tax, then I estimate that theta equals 0.5, like half the people are paying attention. So you can work out the simple math for this equation, but basically that's what it's telling you, that if I compare the effect of that intervention to the price elasticity multiplied by the size of the tax, I end up estimating the degree of underreaction to the tax change, right? So that's one approach. The other approach is very intuitive. You just think about the demand equation. You just compare the effect of a price change with the effect of a tax change, right? So the simple intuition that if I raise taxes by 10% or the gross of tax price by 10% and raise prices by 10%, what's the relative impact of the two? And the ratio of those two, almost by definition, the way we've set this up, is theta. Okay, so we are going to estimate theta using both of these strategies and then map that back to the incidence formulas. All right, let's talk about strategy number one. So we're going to talk about empirical work for a little while before going back to the theory. So the first strategy is an experiment manipulating the salience of the sales tax, which was implemented at a supermarket that belongs to a major grocery chain in the US, has 2,000 stores. So 30% of products sold in this store, like in other grocery stores, are subject to sales tax. And what we did is posted tax-inclusive prices on the shelf for a subset of the products subject to sales tax, which is 7.375% in this city in Northern California. And we use scanner data on price and weekly quantity sold by product in order to evaluate the effects of the intervention. So let me first show you what the intervention was. Okay, so it's very straightforward. When you go to the grocery store, normally you see like this price of $5.79 for this hairbrush or whatever. But that does not include the tax that you pay at the register, right? So we added these signs for 1,000 products that said total price $5.79 plus sales tax equals $6.22. Okay, and so then similarly for like half an aisle of this grocery store for about a 3-week period, right? So it's a very straightforward intervention. You might ask, why did you focus on these kind of trivial categories like hairbrushes and I think it was deodorants and cosmetics? And the reason is that the manager of the store definitely believed our hypothesis going in. And he said, you know, we had said, let's do this on all the taxable products in your store. He said, absolutely not. We're going to lose way too much money if we do that. Okay, so that's why we focused on this subset of products. Now, the other reason for focusing on this particular set of products, you know, they don't generate a tremendous amount of revenue for the store, but the other important thing about them is that they're very elastic. Demand is very elastic. And so when you think about power in an experiment like this, you need something where demand is going to respond a lot to price, right? So if you tax, if you do this with a product like milk, milk is demanded relatively inelastically, so you're not going to have enough power to see anything in the data. So you need to pick something that has a high price elasticity to begin with. Okay, so one thing that's a concern with any experimental intervention like this, or it's a problem that arises very commonly, is that there may be various channels through which your intervention is affecting behavior. So in particular, one concern with posting tax-inclusive prices is that there may have been many channels besides salience, which is the thing that we're focused on, that affected the level of demand. And so there's a common problem in field experiments that's often called Hawthorne effects. So what's the kind of concern here? When you go to the grocery store and you see half an aisle of the store with these 1,000 weird tags that you haven't seen before, you decide, oh, I'm not going to look at that aisle this week. They're doing something strange, and you go somewhere else. What are we going to end up seeing in the data? Demand falls in that period, and it has nothing to do with the information that we're providing here. It's because of some totally different mechanism. Okay, so this is a challenge, I think, in field experiments in general. You'll see that a lot of people spend time trying to show that the channel they're interested in, the mechanism they're interested in, is what's at play. Now, ideally, you'd rule out all other mechanisms. And at some level, this is kind of the advantage, I think, of lab experiments relative to field experiments, where you have a much better handle on what the mechanisms at play are. But in the field, it's really impossible. Like, we have no way of knowing what people were thinking when they saw these tags, right? But I think one thing that is useful, like in your own research to do if you do something like this, is to present evidence that the mechanism of interest is actually very powerful. So what I mean by that is the following example. So what we did, because we were concerned about this, is to just try to show some evidence that the tags were having at least the intended effect that we expected in a very strong way. So the way we did that is to take the undergraduate public finance class at Berkeley that I was teaching, and we showed them this image, or an image like it, and we asked them to pick two products that they liked and write down the total price that they'd have to pay at the register when they checked out these two products. And so the idea was to first, we showed them without these experimental tags, this image, and then we showed it with the experimental tags. And the idea was to see whether people would remember that you have to pay taxes, and that's what determines the total price at the register. So here are the results of that simple exercise. So with the original price tags, which do not show you the tax-inclusive prices, only 18% of people tell you the tax-inclusive price, the total tax-inclusive price. When you put on the experimental price tags, where now they see the taxes directly, that number jumps up to 75%. Now, you wonder why it doesn't jump up to 100%. I guess that shows you 25% of undergrads can't add two numbers. But anyway, the point here is that there's a big first stage impact, right? So while I can't show you that this experiment didn't have other effects, it's at least clear that within this population, it does have a pretty big effect on what your perceptions of the price are, right? So I think doing something like that is useful in addressing these concerns. But you can never totally, I think, be sure. Okay, so what's the research design that we use to analyze the impacts of this intervention? So the way we think about it is that the treatment group is defined by three dimensions. The set of products that we change the tags for, these 1,000 products. The store in which we did the intervention, one large store in Northern California, and the period during which we put up those tags. Conversely, you can think about three counterfactuals, or three dimensions of control groups. Again, products, so other products in the same aisle. So for instance, we did not change the tags for toothpaste, skincare, or shaving products. Other stores, so prior to the experiment, we identified two other stores that had very similar demographic characteristics and patterns of demand, also in Northern California. And other time periods, of course, right, prior to the experiment, for example. So thinking about those treatment control groups, let me show you how we analyze the data. So what we're using is a quasi-experimental difference and difference technique rather than a pure comparison of treatment and control as you would in a randomized experiment. Why is that? This is not really a true randomized experiment because we did not individually draw which products we would tag and which we would not from like a random number generator. We just picked a certain set of products over a certain period and treated them and didn't treat others. So you could have thought about a randomized design at the product level, like I put a tag on this lipstick but not that lipstick. But we thought that'd be really confusing, right? People would think, why does this one look like it's taxed and the one right next to it is not taxed, and so forth. So that's why we take this approach. All right, so let's think about how we analyze this data. Focus first on data from the treatment store. And what the numbers in each of these cells are average quantities of units sold per week per category. So there are narrowly defined categories in this store like eyeshadow or lipstick or things like that. So the way to interpret this is that they sold like 26 units on average of lipstick per week in the store prior to the experiment. Okay, so the way we're setting up this table is the first row is prior to the experiment, the baseline period. This row is during the 3-week intervention. This column is for the control categories, which we did not tag, and then the treated categories for which we did change the tags. So let's start with the treated categories. What do you see? That when you put on these tags, you have an estimated reduction of 1.3 units in the quantity sold during the experimental period relative to the baseline. Now, you don't want to just use that as your estimate because you worry that there might be other contemporaneous trends in demand, right? So you see lots of fluctuation when you look at scanner data. So for like the simplest example is you see that Coke sales spike right before the Super Bowl, right? So there are lots of like patterns like that. Now, I don't know exactly what the patterns would be with lipstick and cosmetics, but you want to account for potential time series trends. And so the natural way to do that is to look at the control categories, so demand for other products within the same aisle of the store. And you can see that over the same period, demand for those products actually went up by 0.8 units. And so then you can form this difference in difference. So take the difference between these two numbers, or equivalently these two numbers, and that's the so-called difference in difference estimate of the impact of the intervention. How did demand change for these treated products relative to the control products over the same period, right? Okay, so that gives you an estimate of about a 2-unit reduction relative to a base of 25. That's about an 8%, something like an 8% reduction in demand with a standard error of 0.64, which we will come back to in a second. Now, what is the identification assumption underlying that difference in difference estimator? What has to be true for that to be a consistent estimate of the impact of the treatment? So what about the counterfactual?
You need to be able, the counterfactual cannot have a treatment effect. You need to be able to measure the counterfactual.
So that's right. The counterfactual can have a treatment effect, but we need a particular thing to be true about the counterfactual relative to the treatment group.
Same trends.
Yeah, same trends, right? Which is related to the fact that you can't have any sort of treatment in the counterfactual. So what's commonly called a common trends assumption is that in the absence of the experiment, we would have seen the same trend, the same change in demand in the control categories and the treated categories. That's what's critical in a difference in difference analysis. Now, how can we evaluate whether that assumption holds or not? One natural way to do that is to look at the control stores where we had no intervention, and we can do exactly the same analysis. Look at the change in demand in the treated categories and the control categories over that period. And here you see that the difference in difference estimate is actually 0, quite reassuringly. That is supporting the common trends assumption, right? That the changes in the two groups would have been the same had we not done the intervention. And then you can form what we'll come back to later called the triple difference estimate, which is just comparing this with that, which naturally is the same as the DD because you're basically subtracting 0 here. What would be concerning if people is if there's some confusion about whether the treatment applies to the control group or not, and that I'm not sure what we can do about that. What I think is less concerning from the point of interpreting, of just convincing yourself that there is a treatment effect, is that there might have been substitution toward the control categories relative to the treatment categories. Now, the way I think you want to think about that is it affects the interpretation of the estimate. You're estimating some sort of substitution elasticity between the treated categories and the control categories. Now remember that my primary goal here is just to reject the null hypothesis that showing you tax inclusive prices for these goods really doesn't have any, should not have any effect at all, right, as in the neoclassical model. So if the elasticity is what it is because of substitution or some intertemporal shifting or whatever else, at some level it doesn't affect the main objective of this paper, but you're right that it does affect the interpretation of what the magnitudes look like. I've reported standard errors here which are based on a parametric specification with clustering. I want to make a comment about that because I think it's very important in this type of empirical work. Okay, so the thing that you need to be aware of, which is familiar from a basic econometrics class, is that any standard error computation always involves some assumption about the error structure of the data. So for instance, we think that purchases across products within a store week category cell, that's the level of the intervention here, are likely to be highly correlated, right? So in periods when demand for Coke goes up, demand for other sodas might go up as well. And I don't want to treat those as IID observations. If I treat them as IID observations, I overstate my precision because I'm pretending that I have a separate data point for each of those, right? So I want to clearly want to allow for correlation purchases across products within these cells, and we do that in the standard errors that I report here by clustering at that level of store week category. But it's not totally clear that that's adequate. And what I mean by that is, to take an example, suppose we think that there might be correlation across stores or across categories, right? So it could be like you were sort of giving an example of that where when demand is high in this product category, demand is lower for some reason in other categories because people have like a fixed budget and they want to spend, let's say, $100, and so they end up spending more here and maybe less there. There are all kinds of potential correlation patterns in the data or even across stores that this approach of clustering at the store week category cell level may not take care of, all right? And so the generic problem is that the appropriate level of clustering is often unclear. So what I want to talk about is a different approach, a non-parametric permutation test that deals with this issue and is, I think, a very useful thing to have in your toolkit. So this is what's sometimes called Fisher's exact test. The reason it's called an exact test is because it doesn't rely on asymptotic theory to compute confidence intervals. It's exact. The p-values are exact even in finite samples. And you'll see why that is when we talk about how it works. Okay, so the way you do this is really very simple. You pretend that the intervention occurred in each of the other cells of your data. So this is what we'd call placebo tests. So remember that here the data is defined by a store, week, and category. So imagine I take all the other store, week, category cells in the data and pretend that I did the experiment in those cells, okay? For each of those cells, I can recompute the DDD estimate or the DD estimate, whichever you like. So basically, rerun your entire analysis on the other cells of your data, all the other cells of your data, okay? Then you simply calculate where your actual treatment effect lies in the empirical CDF of the placebo treatment effects. So I think this is actually a very intuitive way to think about inference. Let me show you how it works in our data. So what this is the empirical CDF of placebo estimates when I just pretend that the intervention occurred in each of the other cells in the data. And so this shows you the distribution of those estimates. And then the red line shows you where the actual empirical estimate falls. And you can see that the p-value is around 0.06. So you get a much higher p-value than you did from the parametric clustering approach where you got a p-value of less than 0.01, precisely because you're putting less structure on the data, right? You're feeding in much less information, so you're going to get a less efficient estimator. But it's much more robust and I think quite intuitive. The way to think about, I think this is the most natural way to think about inference, like suppose I had done a similar exercise at all the other times in the data. What is the distribution of estimates that I would have gotten, and how unusual is the estimate that I'm seeing relative to all the other estimates. So if this red line like fell over here, what we'd conclude is that there's nothing unusual. We might have seen a 1.7 unit drop or whatever, but we often see 1.7 unit drops in this category relative to that category, et cetera, et cetera. So what I want to know is how uncommon is that 1.7 unit reduction relative to other times in the data, and this is a way to answer that directly. Okay. So like any statistical test, a permutation test has an important assumption underlying it, and it is that the treatment has to be truly random. So in particular, the probability of the treatment cannot vary across the cells. So in an experiment, that's true at some level by construction. So like suppose I have these 100 different cells of the data, and I pick randomly which cell to treat. Then by construction, I've designed it so that I'm equally likely to treat all the cells, right? But in many other practical applications, especially in observational data, that assumption may not hold. So take a case where policy changes are endogenous, which is a natural case where you might think about like a diff and diff setting, looking at the impacts of unemployment benefits. We'll talk about these kinds of examples later in the class. So what's the concern here? Unemployment benefits are not changed randomly. They're often changed during recessionary periods, for example, where we feel like we need to help people more. So now, if you do the permutation test, but just randomly assign unemployment benefit changes to all states of the economy and all periods in your data, you're not going to get the distribution of where these changes are occurring right, because they tend to occur in periods where the economy is going into a recession, right? And so you need to be able to pull the thing that you're permuting from the correct distribution that it was actually drawn from. So in the case of an experiment, like the way we apply it, that's actually the perfect setting, because we know we did the experiment at sort of a random time for a certain set of things. For other applications, it's less clear that that assumption holds exactly, but my view is that this is still a very useful test to run as a benchmark, because even in the case of unemployment benefits, true, it may not be the case that the policy changes occur randomly, but if you find that the impact of the policy you're studying still falls at like the 30th percentile, even though that assumption doesn't hold, I'd have a lot less confidence in the fact that you've actually detected treatment effect. So I'd strongly encourage you to do these types of permutation tests. Very easy to do also. Okay, so let's now talk about a second strategy that we use in this paper to establish that salience matters. So just to wrap up on the first thing I should have emphasized. So what do we find, right? We find like significant reductions in demand of about 8% when we make those tax-inclusive prices clear. We then estimate a price elasticity of demand using the price changes, the high-frequency price changes in the data, and then take the ratio of the two the way that I was describing. And I forget exactly what the number is, but something like 80 or 90% of people appear to not be reacting to the tax, because there's about an 8% reduction in demand for this 8% sales tax, and the price elasticity of demand looks like it's roughly 1. So we conclude that basically nobody's paying attention to the sales tax when they're buying these products. Okay, so now we're going to present a second strand of evidence, which we hope complements the first one and addresses some of the weaknesses in the experimental approach. And that is to compare the effects of price changes with tax changes. Okay? So here, we're going to focus on the particular case of alcohol, because it's subject to 2 state-level taxes in the US and is thus well-suited for our question of interest. So alcohol is subject to an excise tax, which is included in the price that you see on the shelf. So it's levied at the producer level. And so when you see $10 for a bottle of wine or whatever, it already includes this excise tax. The sales tax is added at the register, like for all other products that are subject to sales tax, and it's not shown in the posted price. So we're going to exploit state-level changes in these 2 taxes in order to estimate that parameter theta. And we think that this addresses the concern that the experiment may have induced a Hawthorne effect. So often you see a very useful approach in empirical papers is you're going to end up with one approach that has some weakness and another approach that has a different weakness. It's useful to put the 2 together to get a sense of what's actually going on. Okay, so I'm going to show you 2 estimates of demand curves. on the y-axis here is the change in log per capita beer consumption. So think of this as the growth rate of per capita beer consumption. So this is not levels, right? So actually one fun fact that I learned while doing this paper is that per capita beer consumption in the US is 240 cans per year, which was, I thought, strikingly high. And I don't drink any beer, so that means somebody in this room is drinking 480 cans of beer per year, I guess. Anyway, so this is the growth rate of per capita beer consumption at the state level. So the way we get this data is state level measures of alcohol consumption. Why do states have this data? Because they're collecting tax on it, right? So in a setting like this, you want to get data at the level of the intervention that you're studying. So another approach one could have taken is to get survey data on alcohol consumption, right, on individuals, and then look at how these tax changes affect alcohol purchasing behavior. That would have been much, much worse than getting the state level aggregated data, because the state level aggregate is adding up over millions of people, right? So the fact that I don't have the micro data is totally irrelevant here, because I'm only looking at policies that vary at the level of the state. So this is something that I think is very useful to keep in mind. People are often thinking, oh, I need to get the micro level data set. That's actually not true. It depends upon, you really want the data set aggregated to the level of the variation that you're studying. And in some cases, it might be that microdata is the only way you can get that level of aggregation, but in other cases, you might get it directly, like here. Okay, so change in per capita beer consumption on the y-axis, growth rates at the state level, year on year. Change in the gross of tax price of beer with the excise tax on the x-axis, right? Now remember that I've used the gross of gross of tax price on the x-axis precisely because that's what matters from the model, right, in order for estimating theta, as we saw. So you see a clear downward sloping pattern here. This is actually well known in the literature. It just shows you that when you raise the price of beer, people drink less beer, right? There's nothing more in it than that. We're just using the beer excise tax as an instrument. Now look at the same thing with sales taxes on the x-axis. Hold the y-axis fixed so that you can compare the relative slopes of the two. And you can see that there are fewer dots here because there are fewer sales tax changes. But if you look at the center of where the mass of the points is, the thing looks much flatter than it did. This demand curve looks much flatter than it did for the excise tax. And theory would say that these two should basically be the same as each other, which they're clearly not. Again, people seem to be underreacting to this tax, which is also increasing the price of alcohol relative to the excise tax, which they don't have to think about. It's already in the price. Okay? So again, further evidence that theta is less than 1. And so then you can think about, once I think you show these basic graphs, you can think about various variants estimating a regression model where you have that same y-axis variable that we saw in the previous graphs, but then now you put the two gross of excise and sales tax, the two tax prices of relevance on the right-hand side together. This is the baseline specification. Then we add some controls for other things that might be varying over time. So this is, again, like basically a diff and diff analysis, right? We're looking at changes in tax policies in one state relative to another and asking how that affects alcohol demand. The identification assumption that requires is, again, common trends, that there would not have been different changes in alcohol demand in, say, New York if it raised the excise tax rate relative to Delaware or whatever. Okay, and then we do a couple of other things, which I'm not going to do. Let me point out one thing here which is useful. Anytime you are interested in looking at the difference between two of these, difference in slopes or difference between two regression coefficients, don't just show that the two magnitudes look different, but actually do a hypothesis test for that equivalent. So in this case, the relevant test is an F test for the equality of those two coefficients, and you can see that you reject at conventional significance levels the hypothesis that they're the same. Okay, so let's now come back to what my objective was in showing you some of this empirical evidence, which is to think about how tax incidence works when you have these salience effects. So let's let x of PTZ and y of PTZ denote the empirically observed demands for the two goods. So as a function of the price and the tax, I'm estimating, using exactly these regressions, I'm estimating what these demand curves look like in the data, right? And I'm stressing here that I'm going to treat these as empirically estimated objects rather than things that we derived from theory or utility maximization. So we're going to talk later about behavioral public finance, and this kind of ties into what I think is an important approach in behavioral public finance of not worrying about what the underlying positive model of behavior is, but instead just going straight from what you see in the data to making some statement about policy. So that'll become clearer in a subsequent lecture, but what I want to emphasize here is treat these two things as things you just ran a regression, you estimated what x of PTZ looks like, okay? And the only assumption I'm going to make is an assumption that has to be true, which is that whatever you buy, regardless of the way in which you perceive taxes, you have to satisfy the true budget constraint, right? So you might think alcohol is not taxed, but whatever you think, you're still going to pay the tax at the register, and you have to satisfy the true budget constraint, right? That makes sense, I think. Okay, so I'm going to leave the supply side model the same as what we started out with in the beginning of this lecture. Firms are perfectly competitive and they're optimizing perfectly. They don't have any of these salience misperception problems. One can obviously relax that if you wanted to. And then the market clearing price is now going to satisfy this condition, DFP comma T equals S of P, right? Not DFP plus T, where DFP is what I'm calling X up here is market demand for good X, okay? All right, so let's now, it's actually quite straightforward given the setup we have. The reason I showed you that two-step graph before is that you can do exactly the same thing when you have these salience effects. So step one, demand curve shifts inward when you levy this tax. Now what's different here, how much does the demand curve shift inward is not determined by the slope of the demand curve with respect to price, it's determined by the slope of the demand curve with respect to tax. Okay, so dd/dt and not dd/dp. And so you can see that the size of E is the size of the tax times dd/dt. And then step two is actually identical to the neoclassical model because the amount that the producer has to cut the price is determined by the sum of the slopes of the supply and demand curves. Now notice here that the slope that's relevant in the denominator is dd/dp, but the slope that's relevant in the numerator is dd/dt. So why is that? Can someone have a sense of why the price elasticity is what's relevant for the second step, but the tax elasticity is what's relevant for the first step? Yeah.
We assume that producers optimize.
We assume that producers optimize, but remember here that I have it y, so that's why we have dsdp, but why do we have dd/dp as opposed to dd/dt?
Because producers care about the price.
So producers, that's right, that's why you have the supply curve, the slope with respect to the price. But the producers are cutting the price, and then we want to know how much demand changes, right? Yeah.
Well, they can only change the price.
Yeah, yeah. So the producers are changing the posted price, and that's affecting demand through the perceived price that the consumer is seeing, D of P. And so that's why when the producer cuts the price, what matters is dd/dp for figuring out where you end up clearing the market. But in determining how much the demand curve shifts inward, I levy this tax that people are not paying attention to maybe, and the amount the demand curve shifts inward is going to be determined by the extent to which they're responsive to the tax, all right? So you can see that you need to know both the tax elasticity of the demand and the price elasticity of the demand. And just coming back here, we estimate both of those, right? Or we can think about estimating both of those in many other contexts. Okay, so what does that simple formula tell you? The incidence on producers of increasing the tax is now given by this equation here, where the only change is that we have dd/dt in the numerator instead of dd/dp. And so then we can rewrite that as this traditional term, which we've known for decades, multiplied by exactly this theta thing that we've been talking about estimating. So that kind of closes the loop back to why I was so interested in estimating that particular parameter empirically, right? And so what do you see now qualitatively? There's some useful lessons. The incidence on producers is attenuated by theta. So we generally think theta is probably going to be less than 1 because people aren't paying attention to taxes. That means that producers are going to end up bearing less of the burden of a tax because the demand curve is going to shift inward less, right? So it's as if the consumer is not as elastic because he doesn't care when the tax rate goes up because he doesn't notice it. The second thing you see, which I think actually makes a lot of sense, is that you don't have tax neutrality, meaning taxes on producers end up having greater incidence on producers than non-salient taxes that are levied on consumers. So the reason I say this makes sense is because what you often hear in the public debate is that companies don't want to have the taxes levied on them. They'd rather have the taxes levied on consumers. Now, the traditional economic theory, the economist would say, it makes no difference. Prices are going to re-equilibrate the market, and the economic incidence is going to be the same. But clearly, people who are involved in these transactions seem to think that that's really not the case. And this is one explanation of why that is. So what's the intuition for what's going on? Let's take a simple example. Take something like your monthly cell phone bill, right? Often you see advertised a price like $39.99, but then there are like $7 or $8 of fees and other stuff, basically taxes added on later. Now, those taxes are levied on the consumer, and so the displayed price that you see that the producer is advertising do not include those fees. Imagine instead that the government levied that $8 surcharge directly on Verizon. Then Verizon would have to advertise a price like $47.99, which is going to reduce the demand for cell phones and force them to cut prices more in equilibrium to clear the market. Whereas here you get to pass the $8 on to the consumer, many of whom don't pay attention to it, and you sell exactly the same number of cell phone plans, right? So you can see why it ends up mattering a lot in equilibrium. Yeah. Okay, so that's how salience affects the basic theory of incidence. Producers need to cut the pre-tax price less, basically, when consumers are less responsive to the tax. And the lesson in terms of what we want to do empirically is that we want to think about both supply and demand elasticities as we were before, but we also want to understand what this theta parameter looks like in various contexts in order to understand incidence. Okay, so let me now set up, we have 5 minutes left, what I'm going to do in the rest of this, most of the rest of this lecture on incidence, which is to talk about 3 actual empirical applications. Stepping back from salience issues, which have only more recently become prominent in this literature, but more traditional questions of what the incidence of various policies look like. So we're going to talk about cigarette taxes, we're going to talk about food stamps, and then we're going to talk about the earned income tax credit. Now, from a methodological perspective, I'm covering these 3 papers because they span a spectrum that I think is useful for you to be aware of. So when you're thinking of an empirical study, I think a good way to approach this, or at least the way I approach the problem, is to consider what the ideal experimental design would be first. Okay, so if I could run a randomized experiment and I want to study the effects of the EITC on whatever, labor supply, et cetera, what is the experimental design that I would run ideally? Okay, now you're often not going to be able to run that experiment. So what is a feasible design that I have in the data that approximates that experiment, and what are its flaws relative to the ideal design? So often that's going to be some quasi-experimental approach, which doesn't allow you to identify exactly the parameters you want or involve some strong assumptions, et cetera. Now, one thing that you will notice here, and I think it's useful to keep in the back of your mind as you're doing empirical work, is that there's often a hard frontier, a hard trade-off between the quality of the research design you have and the importance or novelty of the question you're able to study. So one way I like to show this is think about it like this. So suppose you've got the space of how well identified your paper is and how important or novel your question is. You basically can be at various points in the space, and you want to be as far to the upper right as possible. And so, in general, what we'll talk about, the 3 papers we'll talk about, the EITC paper I think is the most important paper because that's a major policy that's affecting the US economy in complicated ways. The cigarette tax paper is actually going to be much better identified but it's a much narrower market, and I think we'd rather know more about the EITC than how taxes on cigarettes affect prices. So that's going to be more up here. But the point when you're doing empirical work is that you don't want to be on the interior of this set, right? Like you don't want to have something that people have written a dozen papers on, right? So at this point, like there are more than 100 papers estimating the effects of taxes on labor supply. I would say if you're going to pursue that for your thesis, you want to absolutely nail it. You want to have an identification strategy that's rock solid. Whereas if you're doing something which has been explored much less, it makes sense to, even if you don't have as great of a research design, to push forth on that. So we'll talk about those papers in the next lecture.